All right. We don't have any major announcements for this week. Okay, there is no test or quiz tomorrow, so nothing to. Yeah, well, one small announcement is I think I decided to push back the office hours by 10 minutes so that I get some breathing space between my two classes and the office hours. So the office hours are from 12:10 to 1:10 instead of 12 to 1. The same Zoom link and everything. Just if you get in early, just wait. Okay, that's okay. But I think I was kind of fighting for it yesterday to reach back by 12 o'clock. So I think it's easier for me if it is at 12:10. Okay. Hopefully that will work for you. If it does not, let me know. All right, let me just keep a chat window open here. And can people hear me? See me?
Yes.
Okay, good. Thank you. Can you hear me? I don't want to ignore you, because I'm always looking there. All right, yesterday we were doing section 1.4. We finished 1.3. Okay, so I'm not going to talk more about that. 1.4 is the slightly unpopular section, if you will. Okay. So we were talking about first order linear differential equations. So if you have something like a2 x times y prime plus a1 x times y, I think some textbooks write a1 and a0, it doesn't matter, equal to g of x. Okay. You can write this in the standard form by dividing throughout by a2. And you get y prime plus p of x times y equal to q of x. That is what you would need when you start doing these problems. Okay. And this is the standard form for a linear first order differential equation. Again, to solve this, most likely it is not separable, okay, unless you have some very special case where q of x equal to 0 or something. Okay, in general, it's not separable. So the only way to do this without going insane is to combine these two into a single derivative, and that is why we looked at the possibility of an integrating factor. All these were discussed yesterday. I'm just trying to help you recall what we were doing. Okay, integrating factor I of x equal to e to the power of integral of p of x dx. So p of x is the function or the coefficient of y. Okay, it could be a function or a number that depends on the equation. Once you get this without making any mistakes, okay, the guarantee is that once you multiply that on both sides of this equation, I of x times y prime plus I of x times p of x times y some students skip this step because they think they are able to do it without going through that, but then they forget to do this part later. Okay, so just for safety reasons, I would just multiply it on both sides and then make use of this and write these two as a single derivative. That is I of x times y prime. That is a derivation that we did yesterday in class, so I'm not going to go through all the details. Okay. And once you are able to accomplish this, we could integrate both sides, put c, and then solve for y. Integrate and that will give you a general explicit solution in these kinds of problems. Okay. To find C, you need initial values, which in some problems you may find it, in some problems you may not need to do that. So that's where we stop. We will start by doing 2 more examples and then look at some applications. Before we get into all that stuff, do you have any questions about any of that, whatever I've written there? Any conceptual questions? I know some of you still might be a little bit disturbed by why this became this, and that is why you might want to just quickly look at the derivation that we did based on the product rule going back and forth. Okay, that is the whole mystery going on there. All right. So if you don't have any questions, let's do a couple of examples more. And I want you to just try this first, and then I'll catch up with you. So example 1, find the general solution. For x square y prime plus x to the power of 3 plus x times y equal to x square. So it's asking for a general solution, so there is no initial value given. Okay. So can you carefully try that problem? Okay, we have everything you need up there, so you can kind of make use of all the information up there. So before you start doing it, make sure that it's in the standard form. Okay, so that is a critical step. The integrating factor is e to the power of integral of this term. Okay, do this carefully. This is the crucial step, because without this, you cannot finish this. right, so if you do that, you get e to the power of x square over 2 plus the natural log of, if you are not sure of whether x is strictly positive or not, put an absolute value. How do we simplify this? Yeah. Mm-hmm. E to the x square over 2 times e to the power of, yes, so this becomes x, okay, and this is still e to the power of x square over 2. Okay, again, there is no plus c in the integrating factor. We keep our constant for the last step of the process. Okay, you don't keep on adding c's everywhere and then create a mess, right? Let me know if you have any questions about that integrating factor step. Okay. All right, let's keep going. So multiply that term on both sides of the equation, the standard form. Okay. And we get x e to the power of x square over 2 times y prime plus x e to the power of x square over 2 times y equal to x e to the power of x square over 2. And my promise yesterday was that if you have full confidence in your calculation for the integrating factor, okay, what can you do with the left-hand side of this equation now? Yep. Yes. Okay. That's the whole point of this integrating factor business, okay, so that we could combine those two into a single derivative. And if you kind of go backwards into product rule, this is actually a real product rule. You got 3 terms, right? So that's why you got 1, then 2, and 3. And that's equal to x e to the x square over 2. Now you can integrate both sides with respect to x. And the left-hand side just becomes x e to the power of x square over 2 times y equal to x e to the x square over 2 dx. And immediately I put a plus c so that I won't forget it later. Okay. We know how to do this. We did a similar one yesterday. U equal to x square over 2 du is 2x over 2, that is x dx. So the right-hand side becomes x e to the power of x square over 2 times y equal to the integral of e to the power of u du, which is e to the power of u plus c, and u is x square over 2. Oops. And to finish it off, divide both sides by x e to the x square over 2. Okay. That's a universal step because you have this integrating factor always multiplying y. Just you have to divide that on both sides. So y equal to, when you divide this by x e to the x squared over 2, you get 1 over x. C over x e to the x squared over 2. I've seen a lot of students kind of trying to later call this as C1. It's not. Okay. There are actually two terms with x here. That's a arbitrary function of x, not a constant. Okay, so please don't rename it as C1. Okay. All right. So any questions on that one? Okay, one more example. This is where some students make mistakes, and let's make sure that you don't. Example 2. Let's see. All right, this one. Xy prime minus 3y equal to 4 x to the power of 5 cosine of 3x. Yeah, find the general solution to this. And let me give you a hint, which you may not need. You end up doing integration by parts insane number of times. I used to give a similar problem on quizzes in the past, and students used to think that I'm a very cruel person because they end up doing integration by parts 25 times because they made a small mistake. So I hope you won't make that mistake. Okay, try to do this. Okay, so divide x on both sides and to reduce the degree on the right hand side by 1. Okay, so it becomes 4x, so 4 cosine 3x. I'm doing something, you have to tell me if I'm doing it right or not. Okay. So do you see any mistakes? Yes. All right, so this negative should be here. Okay. This is the mistake that creates the difference between you go insane or not. Okay. So if you miss that negative, you're going to miss a negative here, going to miss a negative here. Okay, looks harmless. That makes this a negative. Okay, that is the key thing here. And instead of multiplying x to the power of 3, you're actually just multiplying x to the power of negative 3. Okay, and that's going to be just x to the power of 1. There's a big difference between the two terms now. Okay. If it was x to the power of 7, you would have required to do integration by parts 7 times. And that is where people hate me. Okay. Because I didn't mean to do that, but so just be careful. Okay. So yes, so that is the right answer there, including the negative is the key thing. And you might see this on test number 1 next week. Just watch out. If a problem takes the entire test time or the entire rest of the day for you to solve, something is wrong. Okay, usually problems are set up so that it works out nicely in a given amount of time. All right, so this is what you get. Okay, so let's make sure that everything else is right. Let's also write the left hand side so that things look ready to solve. So we have x to the power of negative 3 times y prime minus x to the power of negative 3 times 3 over x times y equal to 4x cosine 3x. It's mainly highlighting that part. So now that we have made sure that all of us agree that x to the power of negative 3 is the correct integrating factor, this is what we have. And I think at this point, all of you know that this is x to the power of negative 3 times y prime. Okay. We've been through this now so many times. And that's equal to 4x cosine 3x. Integrate both sides. So x to the power of negative 3 times y equal to just when you think everything else is going okay, you see things like this. Is that right? I wish math was that easy, Don't you think so? It will be making all of our lives so easy. I may be out of a job. Okay. So what is wrong here? You need integration by parts. You have to do it once. 1 is not insane. Okay, 2 is probably insane. 1 is not insane. So this is integral of 4x cosine 3x. And this needs integration by parts. Just trying to give you some heads up about mistakes that I usually see in the past quizzes and tests. Okay, maybe students just panic and do it or something. I don't know, but please don't do things like this. And I think we talked about integration by parts yesterday, so I'm not going to go through the entire list of functions. Okay, it should be pretty obvious. U is your 4x and dv is cosine 3x dx. And let's finish it off. So the integral of u dv is uv minus integral of v du. In this case, u is 4x, so du is 4 dx, and v is the integral of cosine 3x dx, which I hope all of you remember how to do these kinds of things. Okay, this is sine of 3x divided by 3. So the 3, if you are taking the derivative, you multiply, and the derivative you divide, right? So that is going to be uv, which is 4/3 x cos x times sine 3x. This is uv minus the integral of v du, and that is where you have to do another integration. Okay, so it's minus 1/3 times the integral of sine 3x times du is 4 dx. Okay, that 4 is going to be out here. And the integral of sine, don't forget, has a negative to it. That's negative cosine divided by another 3. Okay, so it's going to be 4/3 x sine 3x plus 4/9. Okay, because the integral of sine is negative cosine 3x. Yep. All right, and the left hand side was x to the power of 3 or x to the power of negative 3 times y. Okay. And you multiply x to the power of 3 on both sides, so y equal to x to the power of 3 times this entire junk. So that is your final answer. And don't forget the last term is c times x to the 3. Don't do any unwanted things with it. All right, looks like all of you are comfortable with this process. Okay, with or without integration by parts, substitution, okay, those things are just minor inconveniences during the process, but the emphasis is on finding the integrating factor from the standard form. Okay. Any questions? All right, now let's look at the nice application for this. Again, the applications for this course are mostly from science and engineering. Okay. And I put a worksheet on Canvas based on the problems from the section so that I don't have to write all the stories here. So if you're able to access, especially those who are here, okay, if you're able to just pull out that once we start doing the examples, it'll be nice so that we can, or I can save a lot of writing. Okay. People who are online can easily access Canvas. So. But if you don't have a computer, I'm happy to just write down the necessary things. So application of linear first order differential equation. We're going to talk about a tank where two different things are going to mix. Okay. The mixing tank problem. Okay, so let's try to first understand what the setup is, what kind of assumptions we make, and so on. Okay. So we have a tank with two openings. So this is the inlet valve, and there is some kind of an exit valve here. So there is some solution coming into this tank. Okay, it mixes it something inside this tank, and mixed solution flows out. So solution flowing in, mixing with something inside the tank. We'll talk about what it is, and then the mixed solution flows out. As a generic example, just take a solution with just salt and water. Okay, it doesn't have to be salt and or water, but it's easy to just imagine this as an easy solution. Okay. So you can think about salt and water coming in, mixes with maybe pure water or salt water, and then flows out. So what we are trying to solve for is the mass or the amount of salt in the tank at any time t. This amount, it's a mass. Okay, so you can talk about it as grams or pounds. Well, all of you at some point would have come across one of the basic laws of physics or fluid mechanics called the law of conservation of mass. Okay, there is no mass that is being created or destroyed here unless you're doing quantum mechanics or something. Okay, so there should be a good account for whatever is happening here. So the rate of change of this salt with respect to time t should be purely based on what is coming in and what is going out. Is the rate of change of salt which is coming in minus the rate of change of salt coming out. Everything that you write in physics must agree unit wise on both sides, otherwise it's wrong. You cannot write mass per time here and then wrote some other stuff here. Okay, so mass per time should be the same thing in minus same thing out. Now, to define these quantities here, we need to understand what exactly is coming in and what is going out. So let C stand for the concentration of salt in water. So for example, if this water has 5 grams of salt per liter, okay, that is the concentration. It's almost like density. Okay. So the units for concentration would be mass per volume. So you can say that this solution has got 5 grams of salt in 1 liter of water. Okay. And let R be the rate of flow. That means how much volume is passing per unit time. Okay. So volume per time. So if this was 5 grams per liter, and this is probably 2 liters per second or 2 liters per minute. Okay. So there is some measure of how much salt is coming in per unit volume and how much unit volume is passing per unit time. So that is going to give a measure of how much mass is coming in per unit time. So this is going to be equal to the concentration in times the rate in. Okay. Always check the units. So this would be grams per minutes, for example. So this would be grams per liter. And this would be liters per minute. So liters or gallons, whatever units you want to use. So you can cancel the liter and liter, and you have grams per minute. Okay, so unit wise it agrees. And the same thing which is going out. So it's going to be minus C out R out. Okay, so that's a differential equation. Okay, so we are trying to solve for A, and right now it kind of looks messy because we got a lot of things going on here, but at least the left-hand side looks like it's a first order equation. Okay. So let's just write that once more without any clutter. So the differential equation that we just wrote there is dA dt equal to C in R in minus C out R out. The C is a concentration, R is a rate. In all the problems you're doing, you will be given this, this, and this. Okay, always. You're always given. Sometimes that information may be a little bit indirectly given to you, but you need those three numbers to start the problem. Okay, given C in, R in, and R out. So those are numbers. That's good. There is no tricky function or anything. So the equation suddenly becomes a lot more easier to manage. What we don't know is C out. Okay. Because if you know that, there's nothing to solve. Okay. C out is a concentration of salt flowing out. Okay. We don't know what happened during the mixing, so that is an unknown quantity at this point. So C out is the mass of salt that is flowing out, okay, from the tank, right, divided by the volume of the solution in the tank. Okay, so this is the mass of salt in the tank, which is ready to just gush out of there. And this V is the volume of the solution. You should not look for C out in the problem. Okay, that is an unknown quantity. So A is what we are trying to solve there. So our equation now becomes dA dt equal to C in R in minus C out, which is A over V. In general, it's A of t over V of t, because both of them are functions of time, times R out, which is also a number. So this is a number, this is a number, this is a number. Okay, so you can see why this is now a linear first order equation. If you bring this to the left hand side, you get an equation in the standard form. Okay. So you get dA dt plus A of t over V of t times R out, which is a number, equal to C in R in. Okay, so both those sets of terms are always numbers. Okay. This is the unknown quantity A, that's here. We're going to talk about V, okay, and that is going to be the full setup of your differential equation. So the next question is, what is V of t? Okay. We wrote that is the volume of solution that is in the tank ready to flow out, but then how do you find that? So it's a slightly long process now. Okay, we are going to write another differential equation to solve for V. When you erase this nice picture, volume of the solution at time t is given by, remember that the volume is a function of time, okay, and that change of volume as a function of time is because of whatever is coming in and what is going out. So the rate of change of volume is the difference between the rates coming in and the rate that is going out. Okay. this is volume per time, this is volume per time, that is volume per time. So whatever is the difference between those two is creating the difference in volume in the tank. These two are numbers, so don't be scared now. Okay, this is a number, that's a number. You can easily solve this differential equation. So dv dt. So from here you can solve v of t equal to the integral of r in minus r out dt. If r in and r out are the same, the volume does not change. Okay, it's the same as initial volume. So if there is a difference in the rates coming in and going out, that is what is going to create the difference or the extra volume that is generated in the tank. Now don't forget the plus C when you do this. There are two plus C's here. Okay, one there is the one that you get from the volume of the solution in the tank, and the other one when you solve the differential equation at the end. So there are two C's here. This C should be obtained by using the initial volume of the solution. So solve using the initial volume, which should be given in the problem. Okay. This is the thing that you should do first. As soon as you start doing the problem, take care of the volume. Okay. Find the volume function, put your C so that you could input that back into your differential equation. Okay. Without that, you cannot solve it. Okay. So once you have this, put it back there and then solve using integrating factor. That will give you another C. Okay. Now, can you tell me what information will help us find this C? Anyone online? No, you can just try. I mean, it's okay to be wrong. What information will help you find that second C? The first one, it's obtained by the initial volume. What about the second one? Yeah. Yeah, the initial amount of salt in the tank. Okay. So A of 0. This is from V of 0 because you're solving for V. This is from A of 0 because you're solving for A. Okay. And this is the initial amount of salt in the tank. Okay. Once again, the word salt here is used as a generic, whatever substance is mixed into the solution. Okay. It could be some other thing in a given problem, so don't panic. So that is the setup. So the governing differential equation is a linear first order equation. You solve it using integrating factor. Okay, don't forget the C's in both parts of the problem. Okay, otherwise there will be embarrassing results. And most likely the integrating factor is usually a very straightforward function, unlike the ones we have seen in the random examples we did. Okay, this process is pretty simple as long as you don't make any mistakes with the setup. So that is going to be our main task today, okay, for whatever time we have remaining. And if you are not able to finish it, we'll continue tomorrow. This is a huge deal for your test number 1, so please don't ignore this. Okay. Mixing tank problem. It takes some time to do this problem, so please practice this. Before we start doing the examples, let me write down a few special cases. Okay. Special case number 1, if R in is equal to R out. Yeah, that's possible. It's coming in and going out at the same rate. Okay. Who's going to stop me? So dV dt, in that case, based on the equation we wrote there, would be equal to 0. Okay. And you get V equal to 0. And suddenly you're like, oh, I cannot do this anymore. What is wrong? That looks perfectly legitimate, right? How did we end up with this kind of bizarre situation where we are going to divide by 0? What am I missing? Yeah, the C again. Okay. Probably have never seen this term C being so important in your life. So the volume is a constant. That constant is initial volume, so that hasn't changed over time. Okay. So if you started with 100 liters, it is still 100 liters. So if you end up with the question of, oh, am I going to divide by 0? The answer is here. Okay. Special case number 2. Pure water coming in to a tank with salt and water. Okay, that's still mixing. How does this pure water information help us in this problem in terms of the, this C in, R in, C out, R out, all those things? Okay. One of these is a special number based on the pure water thing. What do you think it is? What is the meaning of C in? Let's go back and check this. What is this telling us? It's the amount of, yes, it's a concentration or the amount of salt in the incoming solution. Okay. So if it is pure water, what does that mean? Yep. There is no salt coming in, so C in is equal to 0. Okay. How do we know that? Read the question. Okay. It's a simple thing. It should be there somewhere, hiding in there. Just go through all the lines. Case 3, salt and water into a tank with pure water. What is the meaning of this in terms of whatever we just wrote there? Is something going to change? So this is okay. So C in is not equal to 0. There will be some number. What does this mean? I think somebody online has written the answer. What do you think is equal to 0 here? C out is not 0. When if C out is 0, then there is nothing going on. A of 0 is 0. Okay. There is no salt in the tank initially. Remember, that's an information you need to solve there. Okay. So if there is no salt in the tank to start with, the initial value of salt in the tank is 0. There is more salt coming in though. Okay. This is going to make things bad from at this point, but at t equal to 0, there is no A. What about pure water into a tank of pure water? Now I'm playing games. Yes. C in and C out are equal to 0. So what is the purpose of this problem there? Pure water in and pure water out. Is there any mixing going on? No, no mixing. Okay. So this is not a scenario that you will see because there is no mixing. So just stick with the first 3. Okay. So in a general problem, none of these would be 0. Okay. But in a special case, you will see that in a given problem, one of these or one of these two would be equal to 0. That might make your life a little bit easier. Okay. But you still have to go through the whole process. All right, so that is the setup. So I think I kind of erased the differential equation that I wrote earlier. Let me just write that here again. So dA dt plus A over V, both A and V are functions of t. We don't have to keep on writing it, times R out, equal to C in R in. That is the governing differential equation that you're solving using integrating factor. And then all this information should be given in the problem either directly or indirectly based on some of these numbers here. Okay. All right, so this is not as bad as it looks. Once you see a few examples, you'll get used to it. The first example is usually a little rough because you have to kind of sift through all the data to figure out what's going on. Okay. Any questions about the mixing tank problem, about whatever we have assumed, whatever we have written there? Any questions? All right, so now if you can, if those who are able to, please do it. Okay. Go to Canvas, and if you look under modules, I think I have a PDF file with these mixing problems. There are 4 or 5 of them. So let's do them one at a time. Okay. And to make sure that all of us are experts in this. So for those of you who are online, if I share the screen, I can just show you what it looks like. Okay. This is what it should look like. So, you know. I'm not going to post the solutions for this separately, so we are just going to do this one by one. Okay. So keep a good record of this at least till next Thursday. Okay, so read the question and write down what all information that you are able to understand from there. Okay, there are lots of words, lots of numbers. So those of you who are on Zoom, can you still see the chalkboard if I am sharing the screen, or is it only one at a time? I don't know if that is. Are you able to see the writing as well? You can just. Chat. We can see both. Okay, thank you. So that way I can keep it there and read it. Okay, so let's see the numbers here. First thing you should do is try to just assign some numbers to these things, okay, always. Those are the six things that are kind of ruling this problem, okay. Based on that story there, what do you think C in is? That's a concentration of X coming in. 2. You can assume that it is per liter, okay. Per liter or gallon, yeah. So this is 2, that is 2 grams per gallon. 2 pounds. I know it's not explicitly given in the problem, it's per gallon, but please assume that it is per gallon. Okay. What is R in? The rate at which it's coming in? 3. What about C out? I'm looking in the problem. We don't know. Okay. So don't look in the problem and waste time. C out is A over V. R out. So slowly things are evolving here. And what are the other numbers here? What about A of 0? 5. And V of 0 is 50. So it's always a relief when all the numbers are given to something. Okay, there's nothing that is remaining there, so that you don't have to worry about, oh, why is this given there? All of you okay with this? Without understanding this, you cannot do anything. Well, when the problem was written, whoever wrote that problem on one of the final exams was not careful about putting per gallon. So I've been kind of reminding, I should probably change it in that question. So the concentration is always per volume, so that we don't have to scratch our head over this. So dA dt equal to C in Rn minus C out R out. I'm not going to ask you what is C in Rn, that's 6. Minus C out is A over V, R out is 1, so A over V, or we have dA dt. Move it to the left hand side, you get plus A over V. Okay. Again, these are functions of time. Let me just keep reminding you this. And this is equal to 6. Again, before you start doing the problem, we don't know V yet. Okay, we need to find something for V and then we can start solving it. But this is the setup, and we're going to solve this with the condition that A of 0 equal to 5. Okay, so this is a pretty typical initial value problem, where dV dt is R in minus R out. R in is 3, R out is 1, so that's 3 minus 1 equal to 2. So in the past, students have been kind of concerned about the welfare of the tank, whether it's going to get full and is it about to explode or something. That's not our business. Okay. So we just need to work based on what is given. Maybe the tank is of infinite capacity, who knows? Right? So we just start with 50 gallons. Okay, we don't have to worry about how strong the tank is. So this is V equal to 2T plus C. The integral of 2 is 2T, not 2. And this is where our 50 comes in. Okay. So V of 0 is 50. So C equal to 50. So this is 2T plus 50. And that will go here and make our differential equation complete and ready to solve. All right, so we have dA dt plus A over 2T plus 50 equal to 6, where A of 0 equal to 5. So that is the first part of the problem, to set it up and be ready to solve. Okay, so up to here, if you're able to achieve this, it's a pretty good amount of progress that you've made, because the problem was kind of in the form of a story, and you have converted it into a mathematical equation now. Now we can start solving it using integrating factor. So your P of t, I'm using t here, not x. Okay, so P of t is the, oh, there was some chat. Sorry. Oh, do you want me to stop sharing? I can. So. Are you able to do it now? I wasn't seeing the chat. Okay, so P of t equal to 1 over 2t plus 50. So the integrating factor I of t, okay. I know there is a small adjustment problem in the notation here. We were using x earlier, now it's t, equal to e to the power of 1 over 2t plus 50 dt. Now, there are two ways of doing it, okay, and I would recommend that you just pull a 2 out of here and make your integrating factor a little less bulky. Okay. So e to the power of 1 over 2 times t plus 25 integral of this dt. Otherwise, you have to do a u substitution. Both are correct. Okay, I think this one is slightly easier to handle when we do the integrating factor later. So it's e to the power of a half times the natural log of t plus 25. Remember that t is time, that's always positive, so there's no need for putting absolute value here. Once again, this goes upstairs, so this is going to be e to the power of ln of t plus 25 to the power of a half. You can cancel the e and the log, and you get t plus 25 to the power of half. So kind of a very busy problem. Okay, so it's asked a couple of years ago on the final exam, so I always do this as the first example to show it in its full glory. Any questions on the integrating factor? Now we can go back and use that here. A lot of writing and erasing. So multiply that t plus 25 to the power of a half on both sides of the equation, and you get times dA dt integrate both sides. So first of all, this is now t plus 25 to the power of a half times a of t prime. Okay. That is why we were doing this concept of integrating factor earlier. We could combine those two into a single term, equal to 6 times t plus 25 to the power of a half. Now you can integrate both sides. The left-hand side would be just this block here, t plus 25 to the power of a half times a of t. And the integral of this with respect to t would be 6 times t plus 25 to the power of 3 half divided by 3 half. Okay. And when you divide 6 over 3 half, that becomes I'm thinking 4, is that right? Okay. Let's see. Okay, so at this point, we could try to find the C and get this out of the way. Okay. Remember that you are given at some point a of 0 equal to 5. This is why you should clearly write down what you have instead of hiding it somewhere. Okay, you should be able to retrieve it yourself. A of 0 is 5, so let's do that. So you get, when you plug in t equal to 0, this is going to be 25 to the power of a half, which is 5. 5 times 5 is 25. This is 25 to the power of half times a of 0 is 5 equal to 4 times 25 to the 3 half, which actually is 125. So even if those functions look kind of complicated, it's not too bad because you have 25 to help us out. Plus C. So this is 25 here, and this entire thing is what is 125 times 4? 500. This part is 25. So C is 25 minus 500, which is negative 475. All right, so we have everything now. So A of t, which is what the question is asking for. You can also divide both sides by t plus 25 to the power of half. Will give you A of t equal to 4 times t plus 25, because when you divide t plus 25 to the 3 half by t plus 25 to the 1 half, it becomes t plus 25. Okay. Plus c times, which is minus 475 times t plus 25 to the power of negative 1 half. So it looks like the amount of salt is kind of increasing in an insane way from the first term, but it's kind of pulled back by this term. Okay, kind of keeping things under control. So this is your final answer. If there is anything that is going to create some time issues on your test number 1, it's probably the mixing problem if you don't practice enough. Okay, if you practice and get used to all these small nuances there, it should be okay. But don't wait till the day of the exam to start studying. All right. Any questions on this? Looks pretty okay when somebody else is doing it. You should do it yourself and see if you are able to go through the process. Okay? All right, let's do number 2, and that I don't know how far we'll be able to go. I think we have enough time. Number 2 from the handout. Again, read the question, write down the information, and see if you could do it. Might be easier than this one. Okay, so what is your opinion here? What is C in? 3, R in, 8, R out. Same. C in is 3, R in is 8, R out is 8. What is A of 0? I don't know, right? How do you know that? Yes, it's given it's pure water, right? A of 0 is 0, good. That's why somebody says that you should always read the question. Right? Okay, what about V of 0? 100. All right, let's get going then. We are doing problem number 2. Okay. Just go in that order, 1, 2, 3, 4. Once again, here the rate in and out are the same, so the rate of change of volume is 0. Okay, the volume is not equal to 0. Okay, volume is just the initial volume, which has not changed with time. Okay, that's all that says. So actually makes our problem a lot easier to solve because you have a number for V, not a function. Okay. So it's dA dt. Bring this to the left-hand side to get a standard form, plus 8 over 100 times A equal to 24, and A of 0 is 0. A lot of nice things happening here. Okay. First of all, R in and R out were the same. Second, A of 0 is 0. Okay. Of course, you cannot have C in equal to 0. That will make it kind of useless problem. 8 over 100 is 2 over 25. Okay. So the P of t in this case is just 2 over 25. So the integrating factor is e to the power of integral of 2 over 25 dt. I hope this is not too complicated. Okay, 2 over 25 is a constant. Just pull it out. It's e to the power of 2 over 25 t. All right, so then dA dt, let's multiply this on both sides. So I think this has now become a habit now. Let's take the two terms and put it into one derivative. The integrating factor times the variable prime. All right, now we are good to go. Integrate both sides. Times A equal to 24. Don't forget this, e to the power of kt dt is 1 over k e to the power of kt plus c. Here k is 2 over 25, so when you flip it over, it becomes 25 over 2. All right. And this is equal to 300. Once again, don't forget that A of 0 was 0 because we had pure water in the tank. Okay. So we have 0 equal to 300 plus C. E to the power of 0 is 1, not 0. Okay. So C is negative 300. And we're almost there. Divide both sides by e to the power of 2 over 25. E to the power of 2 over 25 t. And you get A of t equal to 300. This will cancel with the e to the power of 2 over 25 t. And you have minus 300 e to the power of negative 2 over 25 t, because you're dividing both sides by this term. So it starts with the initial volume of or initial mass of 300, and it kind of exponentially decreases with time. So that is not too bad, because you had some special cases there. First of all, R in was equal to R out, and A of 0 was 0. Okay, so the combination kind of worked out nicely compared to example number 1. Any questions on this? All right, let's do number 3 then. There's no question on the chat about any of these, I hope. All these are picked from old final exams, so number 3. All right, I hope all of you know how to extract these numbers. I'm just going to write it down. So 15, 4, 2. My only question to you is, what is V of 0? Is it 50 or 10? 10. Okay. Why is that 50 given there? Maybe there's a purpose. Just like there's a purpose for everything in life. So we'll look at that 50 later. Okay, so the initial volume of the solution is 10. All right. Routine stuff now. C in R in minus C out R out. You can see it gets a lot smoother with practice. Get used to the several bits and pieces of things. Where dv dt equal to R in minus R out. It's not C in minus C out. It's R in minus R out. Okay. That's 2. And since V of 0 is 10, we have C equal to 10. Okay, so let's write what we have. Let's bring that term to the left-hand side, right in the standard form. So dA dt plus 2 over V, which is going to be 2t plus 10. Times A equal to 60. Just like I mentioned in one of the earlier examples, try to do things which might make your life easier later. Okay. For example, in this case, you could write this is 2 over 2 times t plus 5. Not saying that this is always possible. When possible, try to clean things up. That will save you a lot of unnecessary things to worry about with integration and so on later. If you keep this 2, there's nothing wrong. Okay, it's going to get adjusted with your value of C, but this is just easier to handle. Okay. If you want to try it without canceling it, you could try it. Okay. The place where it will kind of self-adjust itself is the value of C. The final answer should be the same. And it's a long problem. Okay, sometimes students lose focus and then they write the integrating factor like this. What is wrong? 1 over this, okay, If you do the other one, you will get a million pounds of salt in your tank at some point because it's a quadratic function. Okay, so you need to be careful with these kinds of terms. Okay. So it's 1 over that, and that will create a logarithm that's going to slow things down. Again, you don't need absolute values for these because time is positive. Okay. You can probably see why I suggested that you cancel the 2 there, because you don't have to worry about exponents and everything later. Okay. So this is just t plus 5. All right. Now let's multiply this t plus 5 on both sides of this equation. I'm just going to write a prime for dA dt. Too much of writing. But the right hand side should be clear, 60 times t plus 5. It's nice if I move down here and all right, so the left hand side becomes t plus 5 times a prime. That's the integrating factor, and that's equal to 60 times t plus 5. Integrate both sides with respect to t, and you get t plus 5 times a. I'm going to write two things here. Okay. Tell me which one is correct. So I could write t plus 5 equal to u. Really want to. Okay. So this will be the integral of t dt, or integral of u du, which is u square over 2. Okay. Or I could do it just term by term. Integral of t is t square over 2. Integral of 5 is t. Which of these is correct? I always find this question with all kinds of. So somebody says first. Okay. What is the second one wrong? Or somebody said both. Both are right. Okay. It's your choice. This one and this one are correct. Then how do we maintain the sanity of the answer? We should only have one answer in math. This is not political science, right? So how do we maintain the uniqueness of the answer at the end? Whether you do this one or maybe you do this one, you do this one, but at the end of the day, the answer should be the same. The C should adjust it, right? So the C will adjust any small difference. I prefer this because it's a lot cleaner, but if you want to do this, that's okay. The only problem is that if you compare the values of C, they look different because they are two different functions. But later, if you find the value of A at a particular time, okay, that should give the same number for both of us. So in case your high school teacher did not tell you what C does, okay, it will adjust any numbers in the integration carefully and make sure that the answer is always just one number. Okay. So I'll just stick to the first one. 60 over 2 is 30. So we have t plus 5 times A equal to 30 times t plus 5 whole square plus C. Okay. Now, if you prefer to do the second one, it's nothing wrong about it, but your C will look different. A of 0 is 500. So it's going to be when t equal to 0, that's 5, 2500 equal to 30 times 25 plus C, and this is 750. So C is, I want to say 1750, is that right? And divide both sides of the equation by t plus 5. You have t equal to 30 times t plus 5 plus 1750 divided by t plus 5. Just in case you're going to wonder later, oh, how did he write that? It's because I divided both sides by t plus 5. All right, so that gives you the amount of salt at any time t. But if you read the question, that is not the ultimate thing it's asking for, right? What is it asking for? Asking for the time at which the tank begins to overflow and the concentration of salt in the tank at that time. So this is the mass of salt at time t. We need to do two other things here. You don't have to be a calculus or a mathematics expert to answer my next question. When does a tank overflow? In a tank, when does a tank overflow? Yeah, when the volume just reaches the maximum volume. Okay, now you see why that 50 is given there. Right? When the volume as a function of t becomes equal to the maximum volume, that is when the tank overflows. Okay. There's a purpose for the 50, and that's because we want to know when it's going to spill over. And V of t, we found it earlier as 2t plus 10. Okay, don't cancel the 2 in that one. So 2t plus 10 equal to 50. So t equal to 20. And the units would be 20 minutes, I think. Yeah. Right? So that's just from common sense, right? The volume is equal to the maximum volume. It overflows. Okay. Using that, we could find the mass of salt at time t. So A of 20 could be found there. That's going to be 30 times 25 plus 1750 over 25. This is the mass of salt at time t equal to 20. Okay. Can you tell me what this number is? It is a clean number, I think. 820 grams. Okay. The concentration is the mass divided by the volume. Okay. The volume when it's overflowing is 50. So the concentration of the tank, the concentration of the salt in the tank at t equal to 20, that is when it is overflowing, is A of 20 divided by 50. Okay. Mass divided by volume. A of 20 is 820 divided by 50. Which is around 16.4. Not exactly 16.4. The units would be grams per liter. So the difference between mass and concentration is one is divided by the volume, the other one is just pure mass. We'll do problem 4 tomorrow. Okay, that is a little bit more trickier in terms of the integrating factor. So that's why I kept it to the last one. So that's how we'll start tomorrow's lecture, and we'll also start on chapter 2. But in terms of the test for next week, it will cover sections 1.3 and 1.4. So separable equations and linear first order equations. So that is on May 20th, not tomorrow. Oh, I thought we went over this. So if there is a separate one scheduled, right? I think you took that survey, so it's at that time. Yeah. It's probably at 12 o'clock or 6 o'clock, whichever you picked. So during, so now that you asked, let me just tell you this. On the days we have test, the Thursday lecture will be shorter by that much amount, so that you don't have to see me for longer times. How many questions are on the test? I usually put around 25 to 30 questions. Just kidding, 4 or 5. Okay. Because I have to grade it, otherwise I would have put more. So it's because of purely selfish reasons, not because of your welfare. Okay. All right. Nope, you don't have to log on. I don't want to keep staring at you when you're writing the test. Just do it at your own, I've got better things to do. So just write it peacefully. I'm going to assume that you guys are not going to collaborate with each other. Okay. So find your own private space and write your test. You don't have to turn your camera on or anything. So, any other questions? All right, that will be the end of today's lecture then. Let me stop recording.